Right, check out. The term what we are looking at is amphoterism. Got it? Basically, we start reading here multiple equilibriums. Okay? Multiple equilibrium reactions. When you have multiple equilibrium reactions, then we say it is having some amphoterism part. For example, you can take something like zinc hydroxide solid and imagine it is getting ionized into solid hydroxide aqueous solution. Okay, let us say this is one equilibrium which is being maintained. Likewise, ZnOH twice aqueous, let's say it is maintaining Zn2 plus Zn2 plus 2 OH minus, or we can also have Zn OH twice aqueous plus 2 moles of OH minus, also forming a complex Zn OH4 2 minus. Let's say the equilibrium constant is K2, K3, or we might also have a case like Zn OH twice plus OH minus will be in, instead of one shot, they might be in two shots. That is ZnOH thrice overall minus. And here with one more part of it, that is ZnOH thrice overall minus plus another OH minus. So that is in equilibrium. Take you ZnOH 4 times 2 minus. Like this is the way you are seeing the reaction equations are being given. Now, if you compare the overall reaction, we cannot say one reaction is only dominant over the other. We can have all the reactions possible. So then what we can say, if at all I have to compare what is the solubility of ZnOH twice solid. In case if I have to prefer what is the solubility here. So the amount of solubility is same as this concentration amount, isn't it? Because this is solid. So whatever be the concentration of ZnOH twice, that should usually become the solubility. But the problem what we can notice is that that amount is again treated with, that is getting ionized into Zn2 plus and 2 OH minus also. And ZnOH twice is also getting converted into ZnOH twice minus as well, and this as well, which means whatever the ZnOH twice solid is present, it is converting into some part of this in an aqueous form, some part of Zn2 plus, some part of ZnOH thrice, and some part into this one. So I can say that solubility of zinc hydroxide is a result of summation of summation of zinc related ions and soluble forms. Now, what are all the soluble forms here? So, the solubility of ZnOH twice solid will be equal to, right, concentration of ZnOH twice aqueous, that is first concentration, plus Zn2 plus concentration plus ZnOH thrice minus concentration plus ZnOH4 2 minus concentration. So point is to figure out the solubility. Every zinc form which is in the ionized form or which is in a dissolved form in the solution, that is the total amount of sum. That is what we call it as the solubility. Now, how do we replace these terms in terms of OH minus or H plus and different other terms? Check out first one. Here, we can notice that K1 is equal to simply Zn OH twice aqueous concentration divided by ZnOH twice solid, because solid concentration is 1 by 1. So K1 value is this much, right? So if this is K1 value, K2 value will be equal to this divided by this. So I can say K2 is equal to Zn2 plus concentration into OH minus square concentration divided by K1, because that is what we learned, that K1 is this concentration. Likewise, K3, what is K3 here? This product ZnOH thrice minus divided by ZnOH twice concentration. ZnOH twice concentration is what we already found it as K1 into OH minus, and K4 will be equal to ZnOH4 whole raised to power of 2 minus divided by K3 into OH minus, correct? Because here ZnOH thrice concentration will be equal to, because how do we get this concentration? From this equation, and that is equal to, sorry. So this entire thing, ZnOH thrice 3 minus, that will be equal to K1, K3 into OH minus. So therefore, I will have this as K1, K3 and OH minus whole square. Okay. So from here, whatever the unknown atom, whatever the concentrations of zinc in brackets, you can get it there and you can write it here. So ZnOH twice concentration, we can write it as K1 plus Zn2 plus concentration will be equal to K1, K2 divided by OH minus whole square plus ZnOH thrice minus concentration is equal to K1, K3 into OH minus plus, here this will be K1, K3, K4 into OH minus whole square, right? So that will be equal to ZnOH4 2 minus, okay? So now you notice that the entire equation of solubility has turned into equilibrium constants and OH minus concentration, correct? This is what is the importance of amphoterism, that you are able to generate the solubility of the salt or solubility of the sparingly soluble compound in terms of either the only H plus ion concentrations or in terms of OH minus ion concentrations. Okay. Now, once you generate the solubility, rest of the equation will be easier to solve. So, for example, here you can notice everything is present in the OH minus of, root of 4 here, because you can see OH minus square here and OH minus square here. When you take LCM, it will become OH minus power 4. So, it will become the 4 order reaction there. Got it? I guess all of you understood how to get into the amphoterism part. Given any soluble salt, make sure you write everything in terms of the dissolved number of ions which are present in the solution. Now that is the similar logic which we need to apply to this question as well. So notice zinc hydroxide is an amphoteric species. That means it can show both acidic and basic nature. So it can, the solid part can ionize into, Zn2 plus and 2SOH minus. Okay. And the same solid part can also take 2OH minus to convert into ZnOH4 minus. Okay. That will be solubility 2. Now here it has been defined solubility 1. S1 is the concentration of Zn2 plus. S2 is the concentration of ZnOH4 2 minus. Now, if the medium becomes excessively acidic, then S2 becomes negligible as compared to S1. And for highly basic S1, S1 becomes negligible as compared to S2. Then the solubility versus pH curve is given. How the solubility and pH curve changes. Correct. Assuming S1 is equal to S2 at this point, then find the pH of the solubility of ZnOH twice solid. Uh, at which it is minimum, and also what is the value of solubility. So these are all the factors that have been given. So let us understand term by term how we can solve this one. Check. So let's write the equations which are being given to us. Okay. So first, these are the two equations. Everybody do it simultaneously with me. Okay. So these are the two equations given. So let me rewrite that. See what we can write. Zn OH twice solid, that is in equilibrium with Zn2 plus aqueous plus 2 OH minus aqueous. That will be written as Ksp. Correct? The equilibrium constant for this is Ksp. And you know that Ksp value will be equal to Zn2 plus into OH minus concentration square. And then you know that Zn2 plus aqueous plus 4 moles of OH minus to give Zn OH 4 times overall 2 minus. Okay. This will be the equilibrium constant K formation, Kf. So Kf value will be equal to Zn OH 4 times 2 minus, and that divided by Zn2 plus concentration into OH minus concentration raised to power of 4. Okay. So this is what we have here. And now if it comes to solubility, correct. So from here we can say that the overall reaction, if I write the overall reaction here, you can see this Zn2 plus will get cancelled. So what do I have? I have this as Zn OH twice solid plus 2 OH minus aqueous. It is going to give us Zn OH4 2 minus. That's it. So that is, sum of these two implies the new equilibrium constant will be equal to Ksp multiplied by Kf. Ksp multiplied by Kf. So from here I can write Zn OH twice OH power 4 whole raised to power of 2 minus divided by OH minus whole square, because this factor is anyway going to be 1. So that will be equal to, yeah, this is only 2 minus concentration. So that is equal to Ksp multiplied by K forward. That implies Zn OH4 overall 2 minus concentration is equal to Ksp into Kf into OH minus whole square. That will be OH minus whole square. So now if at all I have to put the solubility based on the given equations here. So what I can say, the total solubility the total solubility of ZnOH twice is basically converting as much as this quantity into Zn2 plus, and the other factor is ZnOH4 2 minus. And Zn2 plus concentration, I can write it as Ksp divided by OH minus whole square. And ZnOH twice or OH power OH4 raised to 2 minus, that is equal to Ksp into Kf into OH minus whole raised to power of 2, right? So this is the equation, everybody. So total concentration is equal to Ksp by OH minus plus Ksp into Kf into OH minus whole square. All right. And now the question asked is, you are getting a minima here, right? The solubility factor, it is changing with respect to pH, but it is reaching to a minimum value at this particular pH value. So I can say that ds by ds, which is the solubility, change in solubility, with respect to change in OH minus concentration or with respect to change in H plus concentration, is equal to 0 at minimum. At minimum. So at minimum value, if that is 0, so I can say that, so ds by dt and ds by d OH minus, that is equal to uh, differentiation of these two. So that makes it Ksp divided by OH whole raised to power of 3, correct? So that is whole raised to power of 3, minus 2 Ksp by OH raised to power of 3 plus 2 times of Ksp Kf into OH minus raised to power of 1, isn't it? This is what we have when you differentiate that. So differentiate that and equate it to 0, because at minima value, first differentiation will be equal to 0. So as you equate, Ksp will get cancelled, 2 will get cancelled. So what do we have here? So 1 by OH minus whole cube is equal to Kf into OH minus whole raised to power of 1. So which implies OH minus whole raised to power of 4 is equal to 1 by Kf. And 1 by Kf value is given 10 raised to power of 16, right? So go back and check. So Kf value is given as 10 raised to power of 16. Hence, if this is 10 raised to power of 16, so that should be equal to 1 by 10 raised to power of 4 raised to power of 4. Isn't it? So if at all I take the root of it, that 4 will go away. Hence, we will get OH minus concentration is equal to 10 raised to power of minus 4, which implies the pOH of the solution has to be 4, which implies pH of the solution has to be 10 at that minimum value. So at this minimum value, what should be the pH? pH has to be 10. Clear? So this is how you're supposed to figure out what is the minimum pH that is being used, that is being present as the solubility changes here. Okay, so everybody please check it out and try to, if you do not understand any step, please let me know. This is the way to solve it, and finally to get how the pH values.
Sir,
Yes, Beta.
sir, I understood till like above total solubility of ZnOH twice. What did you do from that step?
Right. See, up to this you understood, right? How we get
Yes, sir.
ZnOH2 minus. Now, if ZnOH2 is solid, just like you have some salt, a sparingly soluble salt, okay? Imagine like this, it is like a chalk piece. ZnOH twice is a white color powder only, basically. So imagine it is made out of one chalk piece. You add it to water. How much different ions are present in a dissolved form of it? That which has been released from the same ZnOH twice. How many different ions are present? One is Zn2 plus is present, right?
Huh.
A part of it, what else is present? ZnOH4 2 minus is also present, right? In the liquid solution, which is in a dissolved form. This ion as well as this ion, these are the only noticeable ions as per the equilibrium equations which we have, isn't it?
Yes,
So
sir.
usually आपको, that is what we call it as amphoterism, that we are trying to check out what are all the contributing ions in the solution. So Zn2 plus is contributing, ZnOH4 2 minus is contributing. And how do we get Zn2 plus from this particular equilibrium? How do we get Zn4 2 minus from the second equilibrium? Okay. So
Okay.
using that context, now you write Zn2 plus as this way, ZnOH4 2 minus as this way. And then this will become the total solubility of the zinc hydroxide salt. Now that if at all I differentiate, it has to become zero when it is at a minimum pOH or pH value. And we found that the minimum pOH value is found coming out to be 4. So minimum pH value has to be 10. Clear on that?
Yes, sir.
Now once you know the solubility, you can find out what is the uh, constant solubility value. You just have to substitute that value here. So therefore total solubility now, total solubility S is equal to how much we had, Ksp divided by OH minus concentration. So Ksp value is how much? 1.2 into 10 raised to power of minus 17, that divided by OH minus whole raised to power of 2. So which is 10 raised to power of minus 8, that plus second factor is Ksp 1.2 into 10 raised to power of minus 17 into 1 into 10 raised to power of 16, which is Kf, that multiplied by OH minus concentration 10 raised to power of minus 4 whole square. So that is equal to 1.2 into 10 raised to power of minus 9 plus 1.2 into 10 raised to power of how much it is. This is also minus 9 only. This is total minus 8 here. And that multiplied by 10 raised to power of minus 1. So 10 raised to power of minus 9. So it is 2.4 into 10 raised to power of minus 9. So that is the value of the total solubility. Clear on this part, everybody? So this is one standard J advanced question, which is, in the recent times, they have been asking a lot of times here. So you should know how to figure out the pH value, what is the total solubility, how we can relate with the graph questions. I think now you know. I hope all of you understood that. Please make a note if you have done it. Right. Now, notice the last part which we had left, you know, is polyprotic acids. How to calculate the pH present in polyprotic acid. It's a very small part. Again, let's maybe spend let's another 10 minutes to understand this part. Check. Polyprotic acids, that means acids which can give multiple number of H plus ions. If we have only one H plus ion giving, we call it as monoprotic. 2H plus is diprotic, then triprotic, and so on, polyprotic ions. Okay. So First, let's focus on calculating the pH where you have polyprotic acids given. So we'll start with one example. Example of diprotic acids. Diprotic acids. What is, best other than H2CO3? Carbonic acid. It is a diprotic acid. You know that H2CO3 aqueous will be observed to ionize as H plus ion and HCO3 minus. This is also called as the first acidic dissociation or Ka1. The ionization constant involved is called as Ka1. The experimental value of Ka1 is approximately 10 raised to power of minus 7. This value will be usually given to you. And then HCO3 minus aqueous will also ionize further to give H plus aqueous plus CO3 2 minus aqueous. And that will make it Ka2. So this is the second dissociation of the acid. And that is equal to 10 raised to power of minus 11. Okay. So usually that is what you will understand, that for polyprotic acids, for any polyprotic acids, the Ka1 value will be far greater than Ka2, and Ka2 value will be much farther greater than Ka3, and that will be even farther compared to that of Ka4 and so on. Okay. So the dissociation values will drastically decrease at least by every 1000 units. You can say 10 raised to power of minus 7 directly to 10 raised to power of minus 11. That much decrement of Ka value will be observed. Okay. And now, if at all I write this equation in terms of general concentration terms, then what do we write it? So this equation, I can say this is initially C naught, and then C naught minus X will create this as X and X. But the problem here is this HCO3 minus will not remain constant. So HCO3 minus will again ionize into H plus and CO3 2 minus. So here we have X amount, out of which I can say Y amount is lost to get this as Y amount and Y amount. But since H plus is already present, so this total amount will be H plus is X plus Y. And HCO3 minus, whether you read it in first equation or the second equation, has to be minus Y. And here also the same logic. Here H plus was already present, so that is X plus Y. So these are the concentration terms of H plus, HCO3 minus, and CO3 2 minus. This is for Ka2. Now, if I use these two equations, I can say Ka1 is equal to H plus concentration into HCO3 minus concentration, that divided by H2CO3. So that is equal to X plus Y into X minus Y whole, that divided by H2CO3, which is C naught minus X. Now in such cases, because X will be far lesser than C naught value, we can also write Ka1 is equal to X plus Y into X minus Y. Okay. And if you notice, this would only become X square minus Y square. And now check it out. See, the X value as it is less value, but the Y value is even lesser than that. We can see the second ionization value will be very smaller compared to K1, which means the amount of dissociation is very, very small amount. So that's why. See, as much as JE questions are concerned, this is what we need to take in most JE questions. We notice that Y square is far lesser than X square, which implies Ka1 will be simply equal to X square. So Ka1 is equal to x square. So from here, we know that x concentration is equal to under root of, sorry, x concentration is equal to under root of Ka1. Okay, so you will hardly find that as, uh, you will hardly find the concentration of x anything depend on y. So y is ignorant here. And now if you compare the Ka1 here, I can say that Ka1 is equal to x square minus y square divided by C naught. Isn't it? This is what we have been written. So sorry, this is C naught minus x. My mistake. I have not written that. Yeah. Ka1 is equal to this y square has been ignored here, correct? Divided by C naught minus x. C naught minus x. Okay. Now the same logic I'm applying to the next case also, C naught minus x. In most cases, x value will be far smaller than C naught value. That's why Ka1 is written as x square divided by C naught. Therefore, x square is equal to under root of Ka1, sorry, simply Ka1 into C naught, and x is equal to under root of Ka1 into C naught. And you know that what is H plus concentration? H plus concentration is basically x plus y. But since the y is very ignorant compared to that of x, we can write this simply as under root of Ka1 C naught. So remember, as much as the JE questions are concerned, your H plus concentration is always under root of Ka1 into C naught. Please check the derivation, everybody. This is one thing everybody should practice, how to generate the equations in the case of polyprotic acids. Okay. So first watch it, right? And then try to write it on your own, everybody. Just like how we had a diprotic acid, the same kind of equations can be repeated for triprotic acid as well. So please do that along with me, everybody. Example, if we have triprotic acids. For triprotic acids, how do we calculate the pH or the H plus concentration? As an example, I'm taking H3PO4 as one such case. So in H3PO4 also, H3PO4 aqueous, it will first ionize into H plus H2, H2PO4 minus aqueous. And the equilibrium constant for that is Ka1. And second one implies H2PO4 minus will be in equilibrium with HPO4 2 minus plus H plus, which is Ka2. And third one is HPO4 2 minus will be in equilibrium with H plus and PO4 3 minus. These are the three equilibriums that are existing, K3. And if initially this is C naught, right? None of them was present earlier. Okay, that is where it started with. And then it has become C naught minus some X amount being lost. So that brings you X and X here, right? So that means here we already had some X. Here we already had some X. So through that, we will slowly start losing some Y amount here to form Y and X plus Y amount. And now you already had X, and now recently we found this as, uh, sorry, we already had Y amount here. We already have Y amount here. Out of that, we will have some Z amount being lost. And you notice H plus was already X plus Y, H plus concentration is already X plus Y. And out of which now when the Z loses from here, some Z amount will be formed. So that is plus z will be formed, and for PO4 3 minus, the value will be z. So these are the values you will have. Correct. Now here also you have to represent the same amount of value. So therefore we can write H2PO4 minus is X minus Y, and H plus concentration will be X plus Y and plus Z. Same way here also plus Z. Correct. So to be precise, this is the first equilibrium we are talking about. This is the second equilibrium we are talking about. The last one is that last equilibrium we are talking about. So from here, you can write Ka1 is equal to X plus Y plus Z concentration into X minus Y divided by C naught minus X. Likewise, Ka2 will be equal to X plus Y plus Z into Y divided by X minus Y. And lastly, K3 will be equal to X plus Y plus Z into Z divided by Y minus Z. These are the values you will have. And you know the K1, K2 values also, value wise, you will notice Ka1 value is far greater than Ka2, which is farther greater than Ka3. This is the value of Ka1 and Ka2. And because of that, again, I can say X, Y, and Z are ignorant in front of them. So we can say Y is way smaller value than X, and Z is even much smaller value than Y, and X is way smaller value than C naught. So these are the comparisons you should understand. How X, Y, Z are compared with respect to C naught. Now, putting that into picture here, I can say Ka1 will be equal to, so we can comfortably ignore Y and Z. So we will have this as X into X divided by C naught minus X. And X can be ignored here. So therefore, this will become simply C naught. So X square is equal to Ka1 C naught. So that is equal to X is equal to Ka1 into C naught. This is X concentration. Now come over to Ka2, everybody. So when it comes to Ka2 here, that is equal to X plus Y plus Z, and here it is Y being ignorant. So we can say X multiplied by Y divided by X again. So X will get cancelled, we'll get this as Y. So Y is equal to Ka2. This is the second equation we can get. What is Ka3? Ka3 will be equal to, now Ka3 will be equal to this concentration into Z divided by Y minus Z. So Z can be ignored here. X and Z can be ignored here. So that means it is going to be X into Z divided by Y. Right. So from here, we can calculate what is the unknown concentration, which is Z. Y can be calculated from here. X can be finally calculated from K1 value. That is under root of K1 C naught. So that's how we can calculate what is the value of H plus ion concentration. Now this X is nothing but H plus ion concentration. So please check it out. Everybody, triprotic acid. Whatever we have done it for diprotic, same logic. Yeah, here we have Y minus Z beta. I forgot to write that. Here Y minus Z. Yeah. That Z is ignorant in front of Y. That's why we have deleted. Ayushi, clear beta?
Yeah, sir.
Done, everybody? Now look into the questions. These are all PYQ, previous year asked questions. So please look into it one by one, how the questions have been framed. The first question includes, find the concentration of S2 minus, HS minus, if the initial concentration of H2S is 0.5 and Ka1, Ka2 values are given to us. Okay. Just as a part of practice, everybody, please try to rewrite the equilibrium reactions once again. Please simultaneously do with me. H2S is a diprotic acid. So let it ionize into 1 H plus and HS minus. Okay. So this we can write it as Ka1, and similarly HS minus aqueous will be giving as H plus S2 minus. Now imagine if at all I write in terms of concentrations. So what do I get? C naught minus X, X and X. And now it is plus Y. Sorry, here I'll write down first Y minus, X minus Y. Some amount is been lost. And that will be equal to already existing X plus Y. And here it is. And X plus Y, and here it will be Y. So this is for Ka2. So now notice Ka1 will be equal to, and here H plus concentration should also be written as X plus Y and HS minus as X minus Y. So Ka1 is equal to X square minus Y square divided by C naught minus X, and K2 will be equal to, X plus Y into Y divided by X minus Y. Now try to ignore whatever be the things which can be comfortably ignored. So first one, Y square here, X here, Y here and Y here. So as we ignore that, so what are the values we can get? So we will get Ka1 is equal to X square by C naught. Likewise, K2 will be equal to X into Y divided by X, so which is equal to Y. So Y is that concentration. So K1 is equal to X square by C naught, K2 is equal to Y. Now, what is K1? What is X and Y here? So we require to calculate S2 minus concentration. S2 minus concentration is Y, and HS minus concentration, which is X minus Y. Y is ignorant, so X. So first write down that values. So HS minus concentration is equal to, it will be same as X. That will be X plus Y, and Y is ignorant. So I can write this as X, right? So that X will be equal to under root of Ka1 C naught. Likewise, S2 minus concentration is equal to X minus Y. Got it? Sorry, S2 minus concentration is equal to only Y, and Y is equal to Ka2 values. So that's it. So from here you can calculate HS minus concentration as well as S2 minus concentration. So I guess all of you understood that logic. Please check. Now it is just about substituting the values. I guess that's okay. In the same lines, one more question has been asked. Same, this is asked in this other one more year, not in the same, and it is a JEE advanced question. Check. They have asked like this: find the concentration of H2 minus and HS minus if the same H2S concentration is 0.1 molar, but the pH of the solution is always maintained. Maybe this acid is in buffer solution where the pH is maintained at 3. Okay. If the pH is maintained at 3, how do I calculate the pH? So please notice. I'll borrow the equilibrium equations from the above. These are the same equilibrium reactions, but instead of H plus here, what you need to write is that H plus is a fixed amount. And that H plus is 10 raised to power of minus 3 and 10 raised to power of minus 3. Are you all getting that point? Why? Because H plus is maintained at 10 raised to power of minus 3. So you will always have to write that as a part of that equation. So K1 will be equal to 10 raised to power of minus 3 into x minus y divided by C naught minus x. While K2 will be equal to 10 raised to power of minus 3 into y divided by x minus y. Okay, so check out what are all the factors we can ignore. Y can be ignored. Here x can be ignored. Here y can be ignored. Okay, hence what are the values you are getting here? So you can see Ka1 is equal to 10 raised to power of minus 3 into x divided by C naught. So x is equal to Ka1 into C naught divided by 10 raised to power of minus 3. This is the value of x. And K2 here, if you notice the y value, so y is equal to K2 into x divided by 10 raised to power of minus 3. This will be the value for y. And the question is asked again, same thing, H2 minus and HS minus. So HS minus concentration will be same as that of x minus y, and which is nearly equal to x, which is equal to K1 C naught divided by 10 raised to power of minus 3. Likewise, S2 minus concentration. So S2 minus concentration will be equal to, right. So S2 minus concentration is equal to Y. So Y is equal to K2 into X divided by 10 raised to power of minus 3. So I guess all of you understood how to figure out what is the concentration of any uh, polyprotic acids given. You must know how to figure out the concentration of unknown ions. Please check. Right. Another question which is related to the tribasic acid. This was asked last year, which is about ratio of these ions of initial concentration of H3PO3 is this much. We need to figure out what is the ratio. So you write individually what is K1, K2 and K3, and using K1, K2, K3 values, you will get this ratio of the concentrations. And that's what is being asked. So this is something which I'm leaving it for you to complete that. So it is not difficult. We have run through the equilibrium equations of H3PO4. Use them and try to figure out what is the ratio of this one. Okay. So that's it, everybody. So this is the cases what you need to learn it from ionic equilibrium. So two major parts. One is amphoterism. The other part is polyprotic acids pH calculations, pH and other ion calculations. Okay. So right, let me close it here. Close the ionic equilibrium part here. Just a minute.